Okay, good morning, boys. Last day we have seen the different structure, cyclic structure and open chain structure of glucose. But before that, I must mention one more thing, that is, why do these cyclic structure come for glucose? There are two important chemical properties of aldehyde group which do not match with the Fischer open chain structure of glucose. Fischer open chain structure of glucose shows that presence of a free aldehyde group in glucose. However, when we talk about the chemical test, special test of aldehyde group, 2,4-DNP test, SIPS test and sodium hydrogen sulfide addition product, these three important properties, chemical properties of glucose are not found, not match with the open chain structure of Fischer, which was presented in our last class. That's why the concept of cyclic structure of glucose came, and the cyclic structure of glucose, it shows that glucose actually exists in two cyclic forms, alpha form and beta form. These alpha form and beta form of glucose are known as anomers of glucose. Anomers of glucose. In fact, in aqueous solution of glucose, this alpha form and beta form mainly exist 99.5%. Only 0.5% of open chain structure exists with equilibrium, and that's why the deviation from its chemical properties. Okay, boys, today we shall discuss about the structure of fructose. Structure, chemical properties of fructose are not in your syllabus. Directly structure of fructose will be discussed here. This is the structure which you see here. This structure is given by Fischer. So, this is known as Fischer open chain structure of fructose. Fischer open chain structure of fructose. Now, this is the open chain structure. Here fructose also exists in two anomeric form like glucose, alpha form and beta form. And these anomeric forms of fructose is due to cyclization between the carbonyl group, ketonic group at second position and the fifth carbon, that is 1, 2, 3, 4, 5, the OH group of fifth carbon. So, the cyclization in fructose takes place between C2 and C5. This lone pair of oxygen interacts with carbon and the pi bond breaks. So, what is this? There is a bond that will be formed between this carbon and this oxygen. This hydrogen will be positive and this oxygen will be negative. This hydrogen plus shifts to this oxygen minus to form OH. One more OH group will come here due to cyclization. So, due to cyclization, one more OH group will come here. So, this carbon atom number 2 will have a one OH group and another CH2OH group. Therefore, the Fischer cyclic structure of fructose can be written in this way. This is the carbon atom number 2 and this is converted to OH, this is converted to OH, the another bond, it is attached to CH2OH, it is written here CH2OH, and then you have the last carbon CH2OH, CH2OH, and then 1, 2, 3 lines you give 1, 2, 3, and the pattern is same. The OH group, pattern of OH group, configuration of OH group is similar to glucose, right, right, left, right, right, left. In case of glucose, it was right, right, left, right, because the carbonyl group of glucose at C1, here the carbonyl group of fructose is at C2, so it is the configuration is right, right, left. You have to stop at 3, and in glucose right, right, left, right. Now, so this right takes part in bonding. This is the bonding with oxygen. This is hydrogen. This OH is free here. Here it is H. This is H. This is OH. So, this is the cyclic structure, Fischer cyclic structure of fructose. So, this is Fischer cyclic structure. structure of fructose. So this one is Fischer open chain, this is Fischer cyclic structure. See here the carbon atom number 2, carbon atom number 2 which was the carbonyl group, ketonic group in the open chain structure. Now it has got one more OH. This OH is at the right, so it is given alpha form, alpha anomer. The full name is alpha D because this portion is similar to D configuration of glyceraldehyde, that's why capital D is given. And fructose by nature, fructose is levorotatory. So by nature fructose is levorotatory, so this is minus, this is optical sign of optical rotation. Negative means anti-clockwise, levorotatory, minus sign is given, alpha D minus fructose, alpha D minus fructose, this form, cyclic form. The another cyclic form is similar to this one, C, it is just you convert it, OH left, give OH at the left, CH to OH right, just convert the configuration at C2, OH right it is alpha, OH left it is beta form. Then 1, 2, this is H, this is OH, next one is OH and this is H. The last one, this is the cyclic with oxygen bond, this is H, this is CH to OH. So look at there is no change, only there is a change at C2. In case of glucose there is a change at C1, in case of fructose there is a change at C2. And C2 OH group is oriented at the right, it is alpha, OH group oriented at the left, it is beta. So this is beta D minus fructose, beta D minus fructose. So these are the cyclic structure of Fischer cyclic structure. So remember here, if it comes, write down the open chain structure, Fischer open chain structure of fructose, you have to write this one. This line and this line is not necessary, it is just shown to understand the cyclization. This line and this line is not necessary. In open chain structure, you will write the structure without giving this and this. Now, this is the cyclic structure of fructose, Fischer cyclic structure. Then you have Haworth cyclic structure. Haworth cyclic structure, it is known as furanose. In case of glucose, it was pyranose, and in case of fructose, it is furanose, because the fructose structure is similar to the structure of furan. So see here, this compound is known as furan. This compound is known as furan. This one is furan. So the structure of cyclic structure of fructose, Haworth structure is related to furan. So the structure is known as furanose structure. How to convert? The conversion is very simple. If you want to convert the cyclic structure of Fischer to Haworth structure of fructose, the conversion rule is very similar to the conversion rule of glucose. How to do it here? See it. You just write down the furan ring. Just write down the furan ring without the double bond. This is furan ring. This one is furan ring. And now you write a vertical line 1, 2, 3, 4, 1, 2, 3, 4 vertical line. This is start from here. This is C1. See the numbering. This one is C1, C2, C3, C4, C5, C6. This is the numbering. So C1, C2. So this is C1, CH2OH. C1, C2. This one is C2. OH group is the right, which is at the right, that will go below the plane, similar to glucose. So this will go below the plane, OH. Now this one, H and OH, right at right, hydrogen. So it will go below the plane. This is above the plane. Then at 4, OH is right. So it will go below the plane, OH below the plane. and H here, and the last one, this carbon at 5, this is the carbon atom number 5, and this is carbon atom number 6. Carbon atom number 6, CH2OH, CH2OH, this is 5, this is 6, and here is another hydrogen. So this form is known as Haworth structure. Haworth structure of fructose. So this is Haworth cyclic structure of fructose. Haworth cyclic structure of fructose is related to Furan ring, and that's why its name is slightly changed. This is the alpha form. We have converted the alpha form of fructose to Haworth structure. So it is alpha D minus fructofuranose. So this is the name. So only if the name is given, write down the structure of alpha D minus fructofuranose, then you have to write this structure. Or question comes in this way, write down the Haworth structure of alpha D glucose. So this is the Haworth structure of alpha D glucose. Okay, furanose structure. Remember, the question may come in that way also, in this way also. Furanose is mentioned, that means it is Haworth structure. Okay, if only alpha D minus fructose is given, this means it is cyclic structure of Fischer cyclic structure. So these are the structures of fructose. Remember, the first one is open chain structure. Open chain structure is very important because open chain structure can be easily converted to Fischer structure, can be easily converted to Haworth structure. So see it here, boys. Regarding structure, I must say that after seeing the class, you will practice the structure of glucose and fructose. Very important in your syllabus. You have no more structure of carbohydrate, only glucose and fructose, Fischer structure and Haworth structure. Okay, boys. See, this part is now it is clear that how to write the furanose structure of glucose and fructose. Pyranose structure of glucose and furanose structure of fructose. If you write the furanose structure of beta D fructose, there will be only change in C2. At C2, the OH group is at the left, C2OH group is at the left, so the OH group will go above the plane. So OH group will be here and CH2OH group will be here. Rest will be same. There will be no change in the rest. Rest will be same. So you will practice it. After practicing, you can make yourself sure that you are able to write the structure of glucose and fructose. Okay, boys. So in our last class, we have also seen that anomers. What are anomers? Anomers are the optical isomers which differ in the configuration of what group? Configuration of OH group at C1. This is the anomers of glucose. About anomers of, what are the anomers of fructose? Anomers of fructose are the optical isomers which differ in the configuration of OH group at C2. So this is C2, this is C2 as you know, and in case of glucose it was C1. Now we come to the part of disaccharide. You have 3 disaccharides in your syllabus: sucrose, maltose and lactose. Sucrose, maltose and lactose. These 3 disaccharides in your syllabus. Now write down disaccharides. Sucrose is a disaccharide and the monomer units of sucrose are alpha D glucose and beta D fructose. Alpha D glucose and beta D fructose. This is a disaccharide. See it here. I want to discuss about the structure of sucrose first. Sucrose, I want to discuss it first. Sucrose has two monosaccharide units, glucose and alpha D glucose and beta D fructose. So the cyclic structure of sucrose, how to write? You know, this one is alpha D glucose. CH2OH, Fischer structure, I am writing O, OH, H. First, second, O is right, right, left, right, 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 left, right. Okay, this is C1, C1, C2, C3, C4, C5, C6. Now this is the cyclic structure. You can write here C, first carbon, C, first carbon. This is alpha D plus glucose. I have written Fischer structure, alpha D plus glucose. So alpha D plus glucose, this is Fischer structure. Okay, and sucrose, the monomers of sucrose are alpha D plus glucose and beta D minus fructose. So beta D minus fructose, just we have written the beta D minus fructose. See it here. OH, CH2OH, CH2OH, then right, 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 left. Okay, this is beta. H, H, 1, 2, 3, 4, 5, 6, beta D minus fructose. These are the two cyclic Fischer structure of glucose and fructose, because sucrose is a disaccharide consisting of alpha D plus glucose and beta D minus fructose. The structures are written side by side. These are the structures are written side by side. These are the monosaccharide units. These are the monosaccharide units. The linkage between two monosaccharide units is at C1 of glucose. This is C1 and this is C2. C1 and C2. See, this carbon is C2, this carbon is C1. C1 of glucose and C2 of fructose. The linkage between the two monosaccharide units through C1 and C2. This is the linkage. So just OH and OH interacts to form this OH and OH interacts to form water. This is H2O minus H2A is lost. Therefore, what will be the linkage? C1 O C2. So see it here, water is lost during the formation of disaccharide or trisaccharide or polysaccharide. The hydroxyl groups interacts and then the linkage is formed between the two carbon atoms through oxygen atom. Therefore, see, this oxygen atom is left. Therefore, you can write in this way, this is the oxygen, write it clearly, this is the oxygen. So this one is the linkage, C1 and C2. So C1 oxygen, C2. This linkage between two monosaccharide units, C1 of glucose and C2 of alpha beta D fructose through oxygen atom. This linkage is known as glycosidic linkage. Glycosidic linkage. So we come to know the definition of glycosidic linkage. So what is glycosidic linkage? Glycosidic linkage is the linkage between two monosaccharide units. The linkage between two monosaccharide units through oxygen atom. The linkage between two monosaccharide units through oxygen atom, this linkage has a special name and this is glycosidic linkage. Clear? So what is sucrose? Sucrose is a disaccharide. Sucrose is a disaccharide of what are the monosaccharides of sucrose? The monosaccharides of sucrose are alpha D plus glucose and beta D minus fructose. So what will happen if sucrose is undergone hydrolysis. If sucrose is hydrolyzed, the product will be 2 monosaccharide units. So, see it here, the hydrolysis of sucrose C12H22O11 plus H2O water. So, with water, this water is lost, and if it is treated with water again, this will get one OH, this will get another OH from water, and these two parts will be separated. Glycosidic linkage will be broken down. The glycosidic linkage is affected during hydrolysis. So, when it is hydrolyzed, this is the linkage which is affected. This side one OH, this side another OH. After one molecule of consuming one molecule of water per unit of sucrose. So, this is after hydrolysis, it forms C6H12O6 plus C6H12O6. Okay. So, this is alpha D plus glucose, and this one is beta D minus fructose. Now, one more thing is observed. The observed is change in the optical rotation. Sucrose itself, this one itself is dextrorotatory. Sucrose, this entire unit is not a symmetric molecule, it is an asymmetric molecule. Therefore, it is itself a dextrorotatory in nature, sucrose. But after hydrolysis, it forms alpha D plus glucose and beta D minus fructose. Their optical rotations are different. After hydrolysis, this mixture is levorotatory. This mixture is levorotatory, and this hydrolysis of sucrose or cane sugar, it is known as inversion of cane sugar. Okay, boys, inversion of cane sugar. So, what is inversion of cane sugar? The change in the sign of optical rotation. I repeat, the change in the sign of optical rotation from dextrorotatory before hydrolysis to levorotatory after hydrolysis is known as inversion of cane sugar. The change in the specific rotation of sucrose, from dextrorotatory, because sucrose itself is dextrorotatory in nature before hydrolysis, and to levorotatory after hydrolysis is called inversion of cane sugar, and the these products are known as invert sugar. The products are known as invert sugar. So, these two things you will keep in your memory, that what is inversion of cane sugar and what is invert sugar. Inversion of cane sugar, I have told the definition, the change in the sign of the optical rotation of glucose from dextrorotatory before hydrolysis to levorotatory after hydrolysis is known as inversion of cane sugar. What is the reason? Because this is dextro, this is levo, but the mixture is levo. That means the levorotation of fructose is more than the dextrorotation of glucose. This inversion, after inversion of cane sugar, the product is levorotatory. This is because the levorotation of fructose, beta D minus fructose, is greater than the dextrorotation of alpha D plus glucose, and that's why we see that mixture is levorotatory. The exact values are not necessary. It is dextrorotation plus 52.5 degree and levorotation minus I think 92.5 degree, 92.4 degree levorotation. So, minus 92.4 degree, they are formed in the equal quantities. So, the levorotation of fructose is more than the dextrorotation of glucose, and that is why we see the product after hydrolysis or inversion of cane sugar is levorotatory in nature. Okay, boys. So, this much you will prepare. Then we share other disaccharides before you. Okay, thank you.